Well, good morning. I'm happy to come over and meet with you all this morning. The focus of today's session is mostly on REDD, which I see as just another payment for environmental services, another market-based incentive for conservation and development. And I want you to rest assured that I'm uncomfortable, as some of you mentioned, discomfort with the idea of these market-based solutions and the commodification of nature. I share that concern. There are, it's a slippery slope. There are a lot of dangers in doing this. I mean, after all, it's markets that are causing the problems, a lot of the problems that we face in conservation and development. And then to look to markets to solve those problems is makes sense in some ways, and it's rather scary in other ways. And one of the things that I've become aware of is that academics tend to, in our own little world, tend to think that we have most of the real intelligence in our midst, and then you get out there with these for-profit companies and realize that they're every bit as bright as we are, and they're probably working harder at what they do. And so the idea of working with them to solve these problems that they cause is really challenging. So we're going to go through, without hiding our misgivings, we're going to go through starting with the most basic aspects of climate change and climate change mitigation. Not talking about adaptation, which is the other whole side of this that really deserves a lot of focus. But thinking about how do we reduce net emissions of atmospheric heat trapping gases. And there are among you those who are better at atmospheric chemistry and meteorology than I am, but I thought it would be useful to start out with some very basic explanations of the mechanisms. I think I'm well suited to do this because I struggle with this, and I've taught it so many times that I am trying to, I think a lot about how to explain it in ways that people can understand, whose chemistry is not so strong, and maybe they're a little bit afraid of science. But it's challenging, especially when you're dealing with very diverse audiences, way more diverse than this one. And when you're a believer in free, prior, and informed consent, just how informed is that consent? And that's a good question for college. I'm not going to go there. When people don't understand the basics that I'm going to be presenting now. And the kinds of questions that you get from people who don't work on climate change are alarming sometimes. This is all about oxygen, and the Brazilian rainforest is the lungs of the world and producing the oxygen, and without the forest having oxygen. Well, okay, let's step back a little bit to this molecule, just this one. We are all of the carbon in our bodies comes was this molecule, carbon dioxide, in the atmosphere. With the help of this molecule, which is obviously much more complex, this is a chlorophyll molecule. That carbon dioxide was fixed from the atmosphere, incorporated into a sugar molecule, and then everything else that we are was, through various biosynthetic pathways, constructed of the carbon that was initially in sugar. And then as we respire, that we're breaking those carbon compounds and getting the energy back out of them that plants originally captured from the sun by breaking those bonds, and then we release carbon dioxide. So right now, the concentration of carbon dioxide in this room is somewhere around 420 parts per million. or 0.042%. So it's pretty rare gas. It's pretty remarkable that plants can take this simple compound from the atmosphere when it's so scarce and incorporate it to make everything else that is biological comes from this molecule. Now,
I think that was your head.
Yeah.
Yeah, computer. Did you hit computer?
Yeah.
Pull your chair out.
Oh, it's not gonna happen again.
To log in again.
Okay.
Excellent.
Okay.
Okay.
I thought that we needed this.
All right. So what we're going to be talking about has all about the carbon cycle. And it starts with carbon dioxide and it ends with carbon dioxide, but those carbon atoms spend a lot of time in biological organisms, in fossil fuels, in calcium carbonate and limestone, in the bottoms of oceans, and so forth. But okay, what's important about this molecule is, like all molecules, it's not stationary. Okay? The accepted absolute zero, which is the theoretical temperature at which molecular movements, atomic movement stops, this molecule is dancing, and that's the way to think about it. And like this molecule, chlorophyll, and like the molecules that are in your eyes that are, you can see my blue pants. This molecule and that molecule are stimulated by different wavelengths of light. So think about light as a wavelength, a frequency, but in this case, it's best to think about light as a particle, a photon. And photons come with different amounts of energy. When a photon of the right energy hits this molecule, it excites it into paroxysms of photosynthesis. What happens is an electron is excited to a higher energy level, and then some of that energy is captured in sugar, a long, complicated process called photosynthesis. Now, in your eyes, your eyes are getting stimulated by different wavelengths of light the same way. Well, and hence you can see color or shades of gray. This molecule is also excited by electromagnetic radiation. Particularly, think about it as shortwave radiation. Remember, there's an electromagnetic spectrum. Heat is long-wave radiation. X-rays and gamma rays are shortwave radiation. In between the two is the visible spectrum and also the photosynthetically active spectrum. Now, when shortwave radiation hits this molecule, it gets excited and it jiggles, it dances faster. And as it slows down, the excitation is released as heat. And so as the shortwave radiation from the sun passes through the atmosphere, it hits photons of that light, hit carbon dioxide molecules and excite them. And then when they calm down, they transform that shortwave radiation into longwave radiation or heat. And it's re-radiated to the surface of the planet. Now, that process has been understood for well more than 100 years. There's no question about the physics of it, even though there are doubters. The relationship between temperature and carbon dioxide is easy to demonstrate. One of my favorites is a YouTube video of a Jamaican instructor with two soda bottles. One she fills with carbon dioxide using baking soda, and the other one is just air. And she shines light bulbs at them, has thermometers in them, and the one with carbon dioxide gets warmer. I mean, it's simple as that. So this is the basic physics of global climate change. There we go. So this is the other molecule that we often talk about in regards to climate change, a methane molecule. which is way scarcer than carbon dioxide in the atmosphere, but it's a better dancer. It gets excited more than carbon dioxide by shortwave radiation. In fact, when a methane molecule releases the heat associated with that, the degradation of that energy, its atmospheric heat trapping capacity is 30 times that of a carbon dioxide molecule. So a small amount of methane has a 30 times bigger effect than the same amount of carbon dioxide. So methane in the atmosphere matters. Now, the longevity of methane in the atmosphere is shorter than carbon dioxide, which also matters because this is a long-term process, and that's something else to keep in mind. But we think about the two of them. So here is the process. You've seen this dozens of times. The solar radiation comes in, shortwave radiation, it's re-radiated as long-wave radiation or reflected. Some of it is captured by the atmosphere. It's scattered. It excites those molecules, and they radiate, back radiate long-wave radiation or heat towards the surface. So that's the greenhouse effect. And greenhouse effect is necessary for life on Earth. Otherwise, we'd be at 300 negative something, 300 at Celsius at night and 600 during the day or something like that. It moderates the temperature of the planet. But as we increase the atmospheric concentrations of heat-trapping gases, the planet heats up. And for political reasons, often people recommend not using the word global warming and instead use global climate change. And I can't understand that other than with global climate change, there are some places that don't get warmer, they get colder because of oceanic currents and stuff. But the planet is warming. That's, to me, it's global warming. So I talk about global warming, but I'm often not politically correct. So are there questions about this basic process? Yes. Oh, well, releasing heat. I guess a molecule of methane has 30 times the effect of a molecule of carbon dioxide. That's the important thing in terms of the heat that it re-radiates towards the surface of the Earth. So I'm not an unquestioning advocate of REDD, but it's with us, and global climate change is with us, and the opportunity to do something about it through changes in land use practices, particularly in the tropics, is not a possibility that's going to go away. REDD is currently the best policy approach to getting the mitigation benefits, meaning reducing the net emissions of atmospheric heat-trapping gases, particularly carbon dioxide. And it's flawed, but it's in the process of development. So since climate change is one of the biggest threats to life as we know it, and it's not going away, we are going to be faced, and you all and the rest of your careers are going to be faced with this issue and how to deal with it. And the mitigation side is just half of it. How do you adapt to climate change is the other big half. So in terms of conservation, climate change has caused the availability, or will soon cause the availability of more funding for conservation than any other intervention before. And so it's likely to have a bigger impact on your professional lives than any other process. So understanding the ins and outs of the process and the policies, it seems really critical. Even if you don't end up working directly on REDD, it's going to be with us, or something like REDD. Okay, and the reason is that we have this increasing atmospheric concentration of heat-trapping gases, these greenhouse gases. This is started in the 1950s, measuring with an infrared gas analyzer, which is an interesting machine because what it does is it takes a sample of gas, shoots an infrared beam of known intensity through the gas, and then if there's a lot of carbon dioxide or methane in the chamber, then the amount of infrared radiation that makes it to a sensor is reduced. Just the same process. Carbon dioxide absorbs infrared radiation. So this has been monitored out in Hawaii in a high volcano since the 50s. The annual cycle is curious insofar as it's the amount of carbon dioxide in the atmosphere globally, because carbon dioxide circulates globally, is declines during our summer, and then it goes back up during the winter, and it's a very regular seasonal cycle. And to understand that, you just have to remember that most of the land on Earth is north of the equator. So when you run a line through the middle of that, you see that the big land masses and most of the terrestrial photosynthesis is north of the equator. Add that because you might be asked about it. Show that. Okay. And we also know that as the carbon dioxide concentration goes up, so does the temperature. There are instances when historically, in terms of geological record, when temperatures rose, before carbon dioxide concentrations went up, but there are explanations for that. I probably couldn't come up with them right now, but the connection is pretty clear. The other thing that you need to remember is that the carbon dioxide concentration in the atmosphere now, despite our best efforts to burn all those fossil fuels as fast as we can and cut down the forest, the atmospheric concentration of carbon dioxide, 400 parts per million, is very low. And during last hundreds of millions of years, most of the time, carbon dioxide concentrations were much higher. So back 250 million years ago, when most of those fossil fuels were deposited, carbon dioxide concentrations were 2 and 3 times higher than they were now. And the planet was a warmer place. It's only been in the last couple of million years that we've had ice ages. And this, Massachusetts and Maine were miserable places to live, only for the last couple of million years. Before that, they were subtropical. Still got dark during the winter, but there weren't glaciers, there weren't ice sheets, and so forth. So we're in an anomaly now, in a low carbon dioxide, low temperature world. And so comments like the rate of increase in carbon dioxide in the atmosphere is unprecedented are wrong. No, carbon dioxide has increased more rapidly than it is now. The rate of temperature change and sea level rise is unprecedented. Wrong. 7,000 years ago, sea levels were rising 10 times faster than they are now. So there's nothing unprecedented about it. What's unprecedented is we have all these people living within a few meters of sea level, and so sea level rise is a concern. Right. So the planet is warming, and so we come up with various mechanisms to try to reduce net global emissions of greenhouse gases. And we'll simplify it, just talk about carbon dioxide, because it's usually reported in carbon dioxide units. So important to keep in mind that carbon dioxide circulates globally. We need to talk about net emissions because there's fixation of carbon in photosynthesis. There's storage of carbon in biomass, in soil carbon, in fossil fuels, in rocks, and so forth. So we have stocks and we have fluxes. And what we're interested in is the positive fluxes, those fluxes that lead to increases in net carbon dioxide concentrations in the atmosphere. So REDD Plus is the newest effort by the United Nations Framework Convention on Climate Change to address this issue, to mitigate or reduce net emissions. It replaces the Kyoto Protocol that did not include standing forests. So give you an idea of my involvement in this, I started in the early 90s when the Kyoto Protocol was being negotiated, trying to get standing forests included, and failed in that effort because of Brazil and the World Wildlife Fund, who fought against having standing forests included. Miserable bunch. But what are you going to do? You can't. There are a lot of Brazilians, and the World Wildlife Fund has a budget bigger than most countries in the world. So they fought against it because they didn't want to see forests as being held ransom, and because of issues of sovereignty. And those are both reasonable, justifiable reasons to hesitate about these global conventions. But here we are now in the days of REDD, where not only do we have reduced emissions from deforestation and forest degradation, the modification of plus the role of conservation, sustainable forest management, and enhancement of forest carbon stocks. So those explicitly include the work in which I'm involved, which is improved forest management to increase standing stocks of carbon in forests. So that's how I got involved. I was trying to promote reduced impact logging, which is harvesting timber without causing the emissions of lots of carbon dioxide. I didn't and don't care so much about carbon dioxide as I do about biodiversity and human welfare and worker safety and water quality and so forth. But carbon is the commodity that's on the table for which they're buyers and sellers, and so carbon is the unit in which I've been dealing for quite a while. Now with REDD, complete with all the hesitations about what the downside of this are. Okay. And I think that's the last slide, unless you've taken over my ability to advance slides.
Really?
That's the last one.
Escape out of it.
Okay.
No.
While we're okay, so there are various ways that we could increase the standing stocks of carbon in forests and other ecosystems. We could and do fertilize forests with nitrogen. That would cause them to grow faster, but nitrogen's an issue because of location of water bodies and aquifers and so forth. We could plant more trees. The other side of my career, which I'm happy to talk about sometime, is protecting and restoring savannas. And so trees are a real menace in savannas because they convert the ecosystem. So whenever anybody talks about tree planting, I worry. I also worry because as a land manager, and I go home and I try to practice what I preach. It's really easier to preach than to practice land management. But I personally am responsible for the death of probably 10,000 longleaf pine seedlings, maybe more. So I don't know why I take them out of the box in which I buy them and put them in the ground, because most of them die. So tree planting is costly, and it's often done in inappropriate places for the wrong reasons. And so I worry a lot about tree planting. But okay, for carbon, it's a good thing. So we talk a lot about trees, and that's what we'll be working on today. Is a project, a REDD kind of project, in which trees will have something to do with your intervention, your REDD intervention.
Yes.
Oh. Okay. Oh. Okay, you can also talk about soil carbon and methods to enhance soil carbon, and particular forms of carbon that are recalcitrant, that are very slow to decompose. So charcoal or biochar is often discussed as one way of sequestering carbon. If in the right form, soil char can increase water holding capacity and nutrient holding capacity. But remember that charcoal has no nutrients in it particularly, it's just a holder. So that's a possibility, and you might want to think about that, but as a possible intervention.
Sorry to interrupt, but is that like the same mechanism that like Heckenberg talked about?
The tetraprecta?
Yeah.
Yeah, it's the same thing, and there are a lot of groups around the world who are investigating it because it looks like it has a lot of options. One of the challenges is that charcoal or char comes in lots of different forms, and it's a wonderful story. It's a real mystery of how people did it and how we could replicate it and where, but it's could be part of the solution. Let's see.
Yes.
Okay, so what we need to think about is, and we'll be working on this later, I just want to introduce it, is that we have some kind of baseline. You've been reading about this, and a lot of you seem to have a lot of experience with it. There's some kind of baseline. Which is the expected emissions or expected amount of deforestation. And then you have an intervention, and that's fine. And then you have this additionality. I'm starting to use the words that we're all going to be using. Okay, thank you. Very effectively, and we're going to be presenting our estimates, and you're going to use real numbers that are made up. And we're going to help you with those numbers, just so you have an idea of orders of magnitude. In megagrams are tons of CO2 equivalent. So a big tropical rainforest in the biomass, in the living stuff, might have 100 megagrams of carbon, or 300 megagrams of carbon dioxide. We'll clarify all that. Okay, and there are other possibilities, like a restoration opportunity where the baseline might involve repeated harvests, so the carbon stocks go down over time. With the restoration intervention, the REDD intervention, the carbon stocks would increase, and then the project would be eligible for payment for this additional carbon. So we're going to be working with that, some of those ideas and more, but now we're going to shift over to the discussion of the readings. And I did read the summaries, and so I look forward to this, and then we'll go back to work on this.